We are used to biology that moves fast. Up here in the sun, life is a frantic engine of consumption, constantly burning through oxygen and solar energy to rapidly divide and conquer. Drop a few miles straight down, and those biological rules stop applying. Buried deep inside the Earth's crust is a massive, hidden biosphere that operates completely in the dark, without seasons or fresh air. Researchers like Dr. Karen Lloyd study the organisms surviving in these extreme subterranean environments. She calls them intraterrestrials. Calculating the sheer volume of life trapped inside the crust reveals a biosphere that is vertically massive, making the familiar surface world look like a thin biological skin. Reaching this subterranean world requires heavy industrial machinery. Scientists deploy massive drilling ships to punch through thousands of feet of ocean floor, pulling up cores of ancient sediment and rock. Even before the drill hits the dirt, you have to sink past the sunlit upper layers of the ocean. Down at the seafloor, the water is near freezing, the pressure is crushing, and the darkness is absolute. Underneath that seafloor crust, the environment turns actively hostile. Fissures vent scalding, boiling fluids, and the surrounding rock is saturated with heavy metals and toxic chemicals. A zone with zero sunlight, with zero oxygen, and zero fresh nutrients should be a biological dead end. The fact that microscopic organisms persist here breaks our standard scientific models of how much energy a cell requires to simply exist. This data visualization shows two vastly different biological timelines. On the left, laboratory E. coli bacteria double their population every 20 minutes, creating an exponentially climbing curve. On the right, deep subsurface microbes exhibit a flat line, waiting thousands of years to divide just once. These extreme slow-motion survivors are known as aeonophiles. It is a specific classification for organisms adapted to persist across massive geological timescales, rather than standard biological lifespans. Their only food source is ancient, buried organic matter from millions of years ago. It is the biological equivalent of being handed a single pizza at birth and having to make it last for your entire life. To stretch those calories, the microbes bring their metabolisms to a near standstill. They abandon physical growth, channeling whatever tiny scraps of energy they harvest strictly into maintaining and repairing their existing cellular structures. In resource dead zones, traditional biological imperatives like rapid replication are a death sentence. By completely sacrificing reproduction in favor of indefinite preservation, these cells establish an entirely different metric for evolutionary success. Over the span of centuries, complex biomolecules like proteins and DNA naturally begin to degrade. To survive these long stretches, aeonophiles have to deploy highly specialized molecular shields. Trehalose alters cellular water to wrap around and brace folded protein chains. Another defense is NAD+ deacetylation. An enzyme uses NAD+ to strip an acetyl group off a protein, restoring its positive charge to lock tightly onto vulnerable, negatively charged DNA, protecting it. Some intraterrestrials take efficiency even further by abandoning chemical digestion entirely. Instead, they extract free, bare electrons straight from the surrounding rocks, pulling the current through microscopic wire-like appendages on their surface. At the extreme limits of physical endurance, life stops resembling the messy, consumption-driven biology we know. It strips itself down to function like raw, bare metal electrical engineering. Dr. Lloyd's field research reveals a blind spot in how we think about biology. Sunlight, oxygen, and rapid growth are not universal laws of nature. They are simply local biases derived from living on the Earth's surface. The only strict, irreducible requirement for a living system is a free energy gradient. A free energy gradient is a physical difference in energy levels between two distinct areas that a system can tap into to perform work. Think of life as an eddy forming in a moving stream of water. In thermodynamic terms, organisms are just structured systems that capture energy as it flows from high to low, speeding up the creation of entropy or disorder in their environment. Redefining life as a thermodynamic vortex rather than a sun-dependent organism changes the math. If all you need is an energy gradient and a way to exploit it, the habitable zones of the universe instantly expand. The deep crust of our planet is locked in permanent darkness, crushing pressure, and freezing temperatures. These are the exact same conditions dominating the crusts of icy moons and distant rocky exoplanets. By sequencing the DNA and measuring the near-invisible metabolisms of ionophiles, we learn exactly which biosignatures to calibrate our space probes for. We are beta testing our extraterrestrial search strategies here at home. This data physically redirects our telescopes and rovers. Instead of scraping the sterile, irradiated surface of a planet like Mars, we know to drill down into the subterranean layers where liquid water and chemical gradients might still exist. The discovery of a living, breathing interior within our own planet changes how we scan the rest of the solar system. Earth's deep inhabitants provide the specific physiological profile needed to identify life hiding in the dark of the universe.